To this lecture on first order systems. We'll see another example of first order system, the mixing tank or the mixing process. Consider a liquid consisting of containing some solid like a salt solution is being mixed in a process, being mixed in a tank. The initial concentration of the salt in the feed is denoted by Ci, and in the mixing tank its concentration is CO. The volumetric flow rate is Q. So a liquid with the volumetric flow rate Q is mixed in a tank, and its the concentration of the solid in the liquid changes from Ci to C0 in the tank. So this is the process. So these are the variables: Q volumetric flow rate, Ci and CO are the concentration of the salt, which I call as A, some component A, it may be salt or some component, I call it A. So Ci and C0 are concentration of A in the inlet and outlet. V is the volume of the tank. Well, so these are assumptions, and based on which we are going to describe and derive the transfer function. There is no change in volume, the volumetric flow rate is constant. The contents are well mixed, the concentration is uniform throughout the reactor. Concentration is uniform throughout the reactor. The same at C0, the same liquid comes out. So the concentration within the reactor as well as in the outlet feed is C0. Well, write the unsteady state mass balance in terms of mass of A. So this is the mass balance at unsteady state, the dynamic state, when the variables are changing in rate of mass in is volumetric flow rate into concentration. Well, this is concentration is, we'll define these concentrations in terms of mass per volume, something like kg per meter cube. Ci and C0 will define in terms of mass per volume, kg per meter cube or kg per liter or gram per liter, some mass by volume. So we'll write the unsteady state mass balance in terms of mass of A. So the rate in will be volumetric flow rate in the concentration Ci. Outlet mass is Q into C0. This is accumulation d by dt of the mass stored in the tank V into C0. V is a constant, so I've taken V out of the differential. So this is the equation, unsteady state mass balance equation. Now let us write the steady state mass balance in terms of mass of A. At steady state the accumulation term will be 0. So you have only rate in equal to rate out, QCIS equal to C0 S. Subscripted variables are the steady state variables. The steady state variables are denoted with a subscript S, and they are constants. So this is a steady state mass balance, QCI is equal to QC0 S. We call it as equation number 2. Then find the difference of these two equations, one at unsteady state minus the steady state equation. Equation 1 minus equation 2 is going to give me this. Equation 1 minus equation 2 will give me this. On the right hand side, QC0 in minus C0 S plus V of dC0 by dt. I had modified this C0, d of C0 as d of C0 minus C0 S, because C0 S is a constant. This term d of C0 minus C0 S will be the same as dC0. So I had modified, by subtracting I had modified this C0 as C0 minus C0 S. Now introduce deviation variables. The difference between the unsteady state variable and steady state variable is denoted as by capital letters. Capital Ci is a deviation variable of the inlet concentration. Similarly, capital C0 for the outlet. So if you substitute this into equation 3, if you substitute these deviation variables into equation 3, we get ordinary linear first order differential equation. You get a first order differential equation, linear ordinary first order differential equation. So this equation will describe the mixing process happening in the tank. The dynamic nature of mixing process will be described by this first order differential equation, first order ordinary linear differential equation. Now to get the transfer function from this, all you have to do is simply take Laplace transform of this. So if you take Laplace transform, Ci is a function of t. So if you take Laplace transform, Ci, Laplace transform of Ci is Cis, Laplace transform of C0 is this, and this is first derivative. Laplace transform is S into C0 S minus C0 of 0. So this term C0 0, the deviation variable estimated at initial condition, that will be 0, because at t equal to 0, this is C0 minus C0 S at t equal to 0. At t equal to 0, C0 is the same as C0 S. C0 is steady state value. So at t equal to 0, the deviation variable is 0. So deviation variable is 0 at initial time. So if you substitute that here, this term goes. The remaining terms are only this right hand side, Q only Vs. So rearrange this and find C0 S by Cis. You get this Q by Vs plus Q. You get Q by Vs plus Q. This is of the form K by tau S plus 1, right? This Q by Vs plus Q can be made into K by tau S plus 1 form by dividing numerator and denominator by Q, by dividing the numerator and denominator by Q. So if we divide by numerator, if we divide by Q, it is 1, and denominator V by Q into S plus 1. So this is of the form first order transfer function form K by tau S plus 1, and where K is, the gain K is 1 and tau is V by Q. Tau is this V by Q. Time constant is V by Q. So if you substitute the units of V and Q, V is volumetric flow rate, meter cube per second, for example. V is volume of the reactor, meter cube. V is volume of the tank, meter cube. Q is volumetric flow rate of the liquid, meter cube per second. So if we divide the units of tau, we will find time units seconds. K is 1, K does not have any unit because the transfer function relates two variables which have the same dimensions. So thus we find for a mixing process happening in a tank, in a stirred tank, with these assumptions, the process can be described by the first order linear differential equation, first order ordinary linear differential equation, and the transfer function is also first order with a gain K equal to 1 and the time constant tau equal to V by Q. Time constant equal to volume of the tank by volumetric flow rate. Well, that is an example of first order system whose transfer function is derived and shown to be of the standard first order form. Hope you have understood this. If you have any doubts, you can leave your doubts or comments in the comment section. Well, there is a correction because of a small mistake. I probably might have noticed that mistake. Here in the assumptions it is mentioned as reactor. Okay, so it's not a reactor, it is only a tank. Like this is only a tank. This is simply a tank. There is no reaction taking place here. No reaction is taking place in this tank. It is simply purely a physical mixing process. So by mistake it has been mentioned here as a reactor. So it is not a reactor. Please read it as, you have to correct this and read it as tank. So this is a tank. The contents are well mixed. the concentration is uniform throughout the tank. I think when I stated the assumptions and I explained the assumptions, I think I mentioned by mistake slip of the tank reactor, and it was also mentioned here as reactor. It is not a, I repeat, it is not a reactor, it is just a tank where only a physical process of mixing is taking place. Please take note of this correction.